Thank you so much, everyone, for joining. So a little bit of a kind of easy call today. We're not doing anything crazy. Normally we'd have like some kind of demo up, but we do have Alex, Blind Nabbler, is going to be on, aka Goose Handler, depending on how you know him. He's going to be talking about something cool he's been working on that was very intriguing to me. Maybe Alex, you can just keep it high level, talk a little bit about what you're working on, what you're trying to solve, and then maybe even show off some of the syntax of the code as much as you want. I'll let you take off from here if you're ready.
Yeah, sure. Sounds good.
Thank you.
So first off, just to kind of like gauge the room, I recognize some of you guys, but could you like raise your hand or do that like Discord notification thing if you guys have built Substreams before? All right. Cool. So, I guess where to start this talk? So I guess a really easy way to start this story is explain kind of a little bit about me. So I am a developer. I've been a developer in the graph ecosystem for a couple of years now, and I've built plenty of subgraphs, and now I've also built a number of substreams. And specifically, I have built, a lot of little substreams, a lot of little subgraphs, but I've also worked on a lot of large-scale subgraphs and kind of protocol-level subgraphs. And I would say that my general experience building large-scale protocol subgraphs, and I think that this can be mirrored by just most people who have built large subgraphs, is that the bigger your subgraphs become, the more random errors can start appearing. This happens kind of from like immutable state and, all the other fun things that come along with that is you can accidentally footgun yourself pretty hard. And I would say that, this whole experience left a pretty bad taste in my mouth a lot of times when working on large protocol subgraphs. I just found it to be a relatively tedious practice where I was just like, accidentally blowing my leg off all the time. I'm sure that I'm not the only person who's blown their leg off doing subgraph development. But like the 15-minute, restart windows are just makes it not the most fun thing in the world. So I guess a lot of these problems were solved and, have been solved really well by the people at Streaming Fast. So Streaming Fast enables a new backend for subgraphs effectively, which are substreams. And substreams are these massively parallelizable little modules. And the way that this works is basically you have little modules, which at some point in the chain take in some raw block data. They are going to apply some transformation to them, much like a pure function or something. And then they're going to spit out some other form of structured data. And this is really nice for a couple of reasons. So when you have little substreams, it means that your code is relatively simple because you're just doing some simple, transformations on your input block data. However, it has really big impacts when you're doing very, large scale data indexing, right? So if you're indexing a whole protocol with substreams, because of the isolation of each of these modules, it makes it a much nicer experience and much less error prone. Basically, this is just because of the lack of side effects with these sort of substreams modules. And the reason why I'm talking about this is, in my opinion, a really great example of a tool that tames complexity. Because I think that the primary issue that a lot of tools have is they just don't offer good ways to tame complexity. And so, what is complexity? There's a bunch of different ways that you can have complexity build as a developer. And I think that as a developer, complexity is our eternal nemesis, if you will. So yeah, where does complexity arise? So, there's a lot of things which have kind of weird complexity graphs, I guess you can say. So oftentimes a lot of easy tools may have a lot of initial, a real lack of complexity in the initial bits, but doing complex things difficult. And I think like a great example of this is something like a GUI. Like GUIs are really good for doing simple things because they make it very obvious on where everything is. But if you want to do anything very complex, the command line is like a way better example because the command line is way less complex for more complex stuff. It has good ways of taming complexity there. And so throughout my experiences building subgraphs, I guess here, let me like kind of take a couple steps back and let's retrace our steps here. So we have me as a developer building subgraphs, and we've realized that, okay, subgraphs have inherent complexities due to mutable state that comes up when you start building large subgraphs or reasonably complex subgraphs. And this is annoying because it forces me to shoot my leg off. Then in comes substreams, and substreams are a much, much better solution because substreams don't have side effects. So substreams successfully gave us tools to be able to manage complexity. And so we just like hurt ourselves a lot less. However, I just found myself realizing that I was, and maybe complexity isn't even the right word, but frankly, I was just kind of getting annoyed. I don't know if that's like the most professional word in the world, but frankly, that's how I felt. With the amount of like sort of redundancy and repeatability or, repeating that I have to do when developing substreams. And so I found myself building a lot of, development tools. So I found myself building little shorthands and Rust macros and stuff to reduce the amount of substreams code that I had to write. And these tools actually got pretty complex. And what I realized was, like these ideas would probably be worthwhile to formalize into a proper language, because effectively what I have done through my course of building all these development tools is I have built myself another language. Because if you looked at the code I was writing when these tools were being developed, is yes, it is Substreams code. Yes, it is, has these handlers on all the Rust code and stuff, but it is effectively a DSL. And thus, the idea of this language called Streamline was born. And basically, what I realized was that, well, I guess like here's kind of the Streamline thesis, which is that substreams are an incredible tool. They are super, super useful. And they are super useful in a lot of ways, which really just like aren't being leveraged yet. So, I guess like clarification and, maybe an asterisk here, because I have some sort of tie here in my business. But, I'm the co-founder of a data analytics platform, and we work with substreams a lot. And we have a lot of really cool things that we want to build with substreams that just aren't possible with these other data sources. And the examples of these are just like you have real-time data streaming that you can use to respond to particular things on chain. And really no other data streaming service has anything remotely close to real time and as easy of a way, I suppose. And so basically I realized I was like, okay, so substreams are extremely powerful. However, they do require learning Rust. And I love Rust. Rust is a great language. Everyone should learn it, but not everyone should really have to learn it for the context of substreams, because it is, a very overwhelming language. And I understand that you'd only need to learn a small section, but basically there's kind of like a disconnect here. So we have substreams, which are written in Rust and operate at a pretty low level of abstraction. And so what does that mean? It means that we have levels of abstraction that all kind of Ethereum devs are familiar with. So we have like high level overviews of, high levels of abstraction for maybe more casual people. And this is stuff like wallets, and you have dApps, right? So Ethereum can be abstracted away, all the implementation details, into wallets and dApps, which are built on the network. And then maybe a developer has a little bit of a deeper understanding of, okay, so dApps are run by smart contracts, and smart contracts have storage slots, and they have these variable types. They have uints, they have strings, they have addresses, blah blah blah. And they emit events and stuff. And this is, I feel like, kind of the level of abstraction that most subgraph developers are familiar with, because subgraphs allow you to operate kind of on this level where you have, these sort of data types that you're working with, that you're familiar with. And then the lower level of things is like, you have lower levels of abstraction, such as understanding that, okay, events come from logs and they have to be indexed. You have index parameters, which are emitted in the particular assembly instruction of, log 1 through 4. And then you also have to ABI decode the data that's present in the log data of something in order to grab it if it's not an index parameter. And these are the types of things that you might have to be aware of to some capacity to work with substreams. And so basically, like, why am I talking about this? The reason why is because I'm just making some observations about the substreams development process, because I love it, but I'm also aware of the blockchain at a lower level than the average Solidity developer is. And so circling back and kind of like highlighting these points, this means that substreams require knowledge of Rust, and they also require a somewhat deep understanding of how the EVM structure works. And so noticing this and noticing kind of some of the patterns that I was doing as when I was developing, is that like the mental model of substreams is extraordinarily simple. It is a very, very simple model where basically you have block data, which is being shoved into these modules and it's being transformed in some way or another. And anyone can understand this. Like if you can understand anything related to Ethereum, you'll have no problem learning this. And so basically I realized, I was like, yeah, this would be great as a language. And specifically, I think that this language should be built to the level of abstraction that most Solidity developers are familiar with. And thus spawned, my language. And so more or less the core thesis of Streamline is substreams are a really awesome tool. They allow you to tame complexity super well, but they have a lot of upfront knowledge required to work with them. And so Streamline is trying to make this as approachable as possible, trying to get substreams in the hands of more developers, and really lower the barrier of entry to substreams without offering a lot of down the road complexity that will, hurt developers in the future. So that's kind of the high level overview. Does anyone have any questions or feedback, or think I'm stupid, or think I'm not stupid? I'm happy to talk anything here. So does anyone have any questions about this, or any of the processes or thoughts? Anything?
I mean, I think it makes a lot of sense. Obviously, I've already kind of seen what you're working on a little bit, but I'm curious, like. For you, you have the experience and you know Rust. You understand the caveats of like the EVM and subgraphs. Do you feel that like something like Streamline is going to be necessary for substreams to really take off and achieve more, adoption? Or do you think that Rust particularly is something that eventually everyone's going to know and the de facto way? Like, I know that's why you built Streamline or building Streamline, but I'm curious what your thoughts are there.
Yeah. And so first off, I would just like to, start this off by saying I'm not a fortune teller. So I don't actually know what's going to happen, but I would say that in its current form, Rust is obviously not a very approachable language. I have worked with developers who have learned Rust for the sake of learning substreams. That's actually initially why I learned Rust. I just happened to also fall in love with it when I learned it. But it's definitely a tedious process, and it's frustrating. And so I think that in the short term, until people start realizing how fucking awesome substreams are, I think that it is definitely a big blocker to the success of substreams because of the high barrier of entry that it requires. Because you can't, expect a random Solidity dev to come across the docs and then be like, oh, this seems like a fun little, toy project. I'm going to go give this a shot, and I'm going to go do this by spending 2 weeks of learning Rust. Like that's a hard ask. And maybe there are people who have done that, and I'm sure that there are, but I personally think that that's just you can't expect something to take off when it has that high of a barrier to entry. And so Yeah, that is definitely part of the reason why I built this, was because, yeah, I want Substreams to succeed, both for my, personal selfish reasons, but then also I'm very interested in having it succeed for other reasons, because Substreams, another fun fact about them, is they benefit from kind of like a network effect. So Substreams are modular, which means you can use other people's modules and you have composability built in. And this is a really powerful thing, because we need more people building modules and we need more people using modules. So that way we can kind of have, I think I referred to it once as a Cambrian explosion of data indexing tools. And this would be pretty kick-ass to have, but unfortunately we're not there yet. And so hopefully Streamline will allow us to get a little bit closer. And I can actually show off some code as well, if you guys are curious, but that's my answer to that question.
I think it would be great if you could show like some of the syntax and some of the, the differences on the approach, right? You're trying to achieve the Streamline, and I think anyone who's even like took a second to look at, Substreams knows that like writing even looking at existing sub, you show off something that'd be good.
Yeah. I'd be happy to. Yeah, and actually, I have a decent amount is actually functional right now, so I can go ahead and share that. But yeah, I didn't get as far into the demo process. I had a pretty great week, but I do have quite a bit of cool stuff to share off. So let me go ahead and share that for you guys. And actually, okay, so this is a Streamline file, and you may wonder, what the hell am I looking at? And it's okay, because I will help explain this. So first off, Streamline files start with a declaration. And what is this declaration? This says what kind of file this is. So there is a special feature which I have not finished implementing yet, but there are stream files which denote a data stream and a data pipeline that you're building. But there is also sync files. And sync files, I can go ahead and kind of like draw this out. Is more or less, it allows you to specify how to use syncs. So maybe if I want to specify, how to use a subgraph, I can specify what modules have to be built in, as well as what data structures should be available to the person building them. So, the graph out sync, when we use a subgraph or a substream to go into a subgraph, you have to implement a particular module called the graph out, and the output type has to be of this particular output type. And I think something like this could be really powerful to have in a module type where you can import it. And much like in Solidity or any other object-oriented language, you can effectively, inherit. I use that word very loosely because I'm not the biggest fan of object-oriented programming. Inheritance strikes fear in my heart. But in this case, it makes a lot of sense, where you can inherit the properties of a sync, and the type checker will help you and yell at you for not implementing things correctly. And we can kind of talk more about this in the future, but let me first, I guess, stay focused here and just show this off. So we start off with a name for the entire module. So this whole thing is called minimal ERC 721. That's just the name of the file. That's all there is. So next, we have valid Solidity syntax here. So this is an interface declaration. And basically this is saying, hey, these are the events present on an ERC 721, or, I can call this whatever, but this is an ERC 721 interface. And so this just tells the Streamline, these things exist and I should be able to use these things. So these allow us to define new data sources to use on chain. And I'll show you some examples now of using this. So here is a example of a map module here in Streamline. Let me just pump down a bunch, and so we can kind of step through this one by one. So let's explain the syntax a little bit here. So MFN, why does it say MFN? The reason why it says MFN is that this is a function which is functioning as a map module. So we said earlier that substreams have this concept of map modules. MFN denotes a map module function. The reason why we said MFN is just because we want to say, hey, this is very similar to a function, but it has some special properties that you'll see here in a little bit if you guys are interested. So basically, we have this module, and we call it burns, and this is the signature. So it takes in, as a data source, an array of ERC721 transfer events. So obviously, ERC721 is the name of the interface. This is the event type that we're using as our input, and it's an array of these things because right now it's currently at the block level. So then what is this thing going to output? Well, it's going to output a burn array. And so what is a burn? Well, a burn is a custom data type that we defined up here. And again, this is using Solidity syntax. This should all feel super similar and super natural for everyone who has worked with Solidity. We just have these like simple struct definitions. So a burn contains a burner, which is an address. It contains a token, which is also, just a uint256. And it contains, this is, nonsensical, but it contains this other field, which is another struct. And I was using this for like code generation testing. But more or less, we have a custom data type here. So to get all the burns on chain, we just say, okay, let's define a module which takes in all the transfers on chain and returns all the burns on chain. And how do we do this? So this syntax here might look like a lot, but I assure you it's really not. Basically, the way that you should read Streamline code is you have a list of instructions to take here in the body. These instructions can be of one of two forms. They can be such as this, which is a higher order function, or they can also be a lambda function. In the docs, we refer to these as combinators, and I can explain why, but more or less, this expression here, the input is going to be the input to the module if it is the first thing in the module, or in the case of here, the input to this higher order function is going to be the output of the previous combinator here. So what we're saying and how you should read this in like a logical sense is we have a module called burns, which takes in an ERC721 transfer array, returns an array of burns. And the way that we get there is we filter through each transfer. And if the transfer.to does not equal the address or address 0, we keep it. Wait, hold on. Does that make sense? Sorry. I was messing with this code a little bit. So we're actually going to filter everything where the transfer.to is equal to the address 0. Sorry. And then for each instance of the now filtered transfers, we are going to say, okay, for every transfer, convert it into a burn. And this is a special function in Streamline that allows us to convert some data type into another one very succinctly. And this is how we declare those. So we just say, convert this type into this type. And this is like the function body. So this is how we actually do this. And so more or less, that's all this module is doing. It's 2 steps. It's very, very simple. We just say, okay, for every transfer that we have, filter it. If it, keep it in the list if the transfer.to is equal to the 0 address, because this will denote a burn in our case, and then map it over to this burn data structure. And so we can actually run this here. Let me go Streamline, or actually, let me just go main run here. This is all written in Clojure, by the way, so it's not actually this slow. It's slow because of the JVM starting up. So just explanation. So we can see here is our generated Rust code for all this stuff. This is not fully complete, but bear with me. More or less, we have our burns module here. And what we do here is we say, okay, here's our input, which is a transfer array. Here's our output, which is a burn array. And we basically just apply these things stepwise. So this is kind of like a compilation process. So we just filter out all the things where the transfer.to is not equal to the 0 address. And then we convert the transfers into burns. And then we can also look at some other stuff. So here's all the type conversions that also get generated for us. So these allow us to do conversions between these array types, which I guess is also one thing I just always missed from working with Substreams was I always got annoyed we couldn't use like array types as inputs and outputs. So our language supports array types as inputs and outputs natively. Yeah, then it just like has all of our nice little like helper functions and stuff. In addition to that, we also have obviously the Substreams YAML. So this is generated for us and it makes all these modules. So under the hood, this is our module our module flow. So we have one module for each of the events that are going to get emitted. So ERC 721 transfer, ERC 721 approval, and all these are being hooked up and wired up to each other, kind of in a nice way. And again, this is not fully complete, so there's a couple bugs here that I'm squashing, but more or less, this whole thing builds an entire substream for you, which is great. And it's great because you don't actually have to know about any of this stuff. So that being said, I guess, yeah, I mean that's kind of the core of how this works for now. I can give some more advanced explanations, kind of, and how you can use it. But let's see. Yeah, the only other thing you can do is you can, in addition to defining map functions using MFN, you can also define store functions using SFN, which again you just kind of use your stuff there to define the signature. The SFN store like that. And you can also define functions, and functions are just non-modules. So they're written the same way. We express the data transformation that we're doing. And that's kind of how you get there. So like this is not doubling the number, obviously, but bear with me. These are like test files. So that's kind of like the core of Streamline in its current form. I will be showcasing syncs and stuff later because that's the really cool feature. But for now, that's kind of a lot of what I have to demo, and I'd be happy to demo other stuff if anyone's curious. Or I can also talk about the implementation, because the implementation is remarkably simple. It is like less than 1,000 lines of code for the primary body. But for now, we can pause it there if anyone's curious or has any questions.
Looks awesome. Very cool. I like everything you guys do there is like enhancing developer experience. And I think this is something that will really help developer experience for Substreams. So excited to see it take off. And how can people get involved if they want to test or, work with you or in any capacity on this?
Yeah. So also, so first let me answer that question. And also I completely forgot a very important part of this that is also part of my reason for writing my own language. So if anyone's curious, they are more than welcome to go to the docs that I'll post here in the chat. So let me, thank you, Mac. Basically, here's the docs for the language, this is the language, but there are docs there. You guys are welcome to go check this out on GitHub if you're curious. You can reach out to me on Twitter, Telegram, Discord, whatever. And I'd be happy to answer anyone's questions regarding this. Obviously, this is like a pretty substantial project. So if anyone wants to help, also like write and implement language features, I'd be happy to get some help there. But it is all written in Lispy closure, so you're gonna have to be happy with parens if you want to help contribute. But so that actually brings me to the second part of this, which is why use Clojure and why implement a new language. The reason why I wanted to use, I guess like one of the benefits of writing this as a new language, as opposed to, let's say, a library for Rust, is that the language, if I have my own language, it means that I get to I get to do a lot of really cool stuff. And one thing that I think is very important for Substreams developers, and this is something that actually I observe, is it's very common for Substreams developers to test by just, building their package and streaming it and observing the data that changes. This is fine for little things because it doesn't use that much data. But in the case of, if you're a normal Substreams developer and you, are working on something large, you're going to run through your data pretty damn fast. And the data is only graciously offered to us 1 terabyte at a time for free by Streaming Fast. And in the case of Pinax, they were very generous and gave us some really nice keys to test stuff with. But this is just wasting data. Like, this is data which should not really be streamed, because the only thing we really care about is the applications of our modules to the block data, and this should be tested locally. So that all being said, is because I have my own language here, I also wrote and am writing an interpreter for the language. Run it without deploying your substreams. So we have two semantical understandings of Streamline. We have the compiled Rust understanding. So we have a path to write Rust code for you, as well as all like the protobuf code and whatnot. But we also have another semantical understanding of the language, which is a live closure REPL. And so this means that you can step through and see how your code is evaluating on each step of your function. You can provide it test data, and you can also pull in raw block data and send it yourself without having to stream this data from a Firehose provider. This will lead to tighter, development experiences, because you're able to immediately see the function application that you're writing. You're immediately able to see if something is going wrong, if you have like a logical error, all without actually using any data that really shouldn't be streamed because you're developing. So that's a really compelling reason I think why Streamline should exist, is because we can have all the benefits of a live interpreted language, while also being able to just compile it to Rust when it's time for like a performance substream. But when you're developing, you don't really care too much. So there we go. That's kind of the end there. So
thank you. That was awesome. Thank you for coming on last minute to talk. I appreciate that, and give a little bit of a demo. So thank you. Any other questions for Alex? All right, great. Well, if there's any other questions, please, be sure to check out Streamline, check out the repo there, and get involved. And thank you guys again for coming. This will be posted on YouTube, so you guys can watch the replay if you think you missed anything or if you came late. Thank you so much, guys, and have a good day.
Yeah, cool. Thanks.